Welcome to the second half of the two-part episodes on Zeroing In with Professor Bhal Chandra Joshi, an astrophysicist based at the National Center for Radio Astrophysics in Pune, whose research work focuses on the study of the very fascinating pulsar systems. Professor Joshi gains his brilliant research insights from the whole spectrum of work that he immerses himself in, from the ends of his experiences on building and maintaining high-end instruments and the GMRT radio telescope facility, through to the surveying, analyzing, and understanding the neutron star and the pulsar systems, among other astronomical objects, and their applications in the real world as pivotal solutions to prevalent questions. In our further conversation with Professor Joshi, we talk about the intricacies of addressing the quintessential questions through astronomy, the everyday experiences of an astrophysicist, and his experiences from the time of building the giant meter wave radio telescope in India, the world's largest in the wavelength range that it addresses. I am Naman Jain, and hosting this episode with me today is Dr. Rashi Jain. This is Zeroing In, the Science Podcast.
So, as an explorer, like you're an observational astronomer, has there been a time when you had like single most memorable observation and it was really fantastic?
Okay, that's a difficult question to answer. There have been several moments. I think one of the most exciting moments was when we observed our first pulsars with a single dish. That is the first observation, by the way, from GMRT. First antenna C3 in 1993 with a very simply made ADC card and a PC. We observed the Vela pulsar. Okay, and that was very exciting because the fact that we can observe these pulsars with a very simple instrument. Today, GMRT is a very complicated piece of instrument, but the thing which I built at that point of time was very simple. And was built from very, very simple kind of electronics which we had, and still we could see the pulsars. So it was very, very exciting. Okay. But another exciting moment which I got was when I was sitting in a telescope in Australia called in New South Wales called Parkes Radio Telescope, and we were doing a survey which was known as High Galactic Altitude Survey. And in the survey, every night we used to observe, and I used to try and analyze the data, and I found this peculiar signal which looked like a pulsar, but yet was not so clear as a pulsar. And I flagged it out and left it for one of my collaborators to go and confirm it, okay, which she did after, say, 3 weeks or so. And we discovered one of the most unique systems known in pulsar astronomy, which is called as a double pulsar system, which has actually provided the most stringent test of Einstein's general theory of relativity to date. In fact, just day before yesterday, there has been a paper on 16-year timing of this pulsar. This was discovered in 2002. Okay, of course, that was a millisecond pulsar, and I did not know it's a double pulsar. I was only happy that it looks like a millisecond pulsar, and lo and behold, I have found a millisecond pulsar. Okay, which till that time I had not searched any millisecond pulsar. I had found some long period pulsars, but no millisecond pulsars. So I was excited by that. Later on, it turned out to be one of the most exciting systems. So I would say not one, but there are two main observations. And this double pulsar later on we observed with GMRT. We are observing even today with GMRT this pulsar, and it shows a very interesting eclipse where it's a binary system. So in fact, it has two neutron stars going around each other. Both of them are pulsars. So when one pulsar goes behind the other pulsar, you see an eclipse. It's a very short eclipse. It's just 30-second eclipse. The orbit of the pulsar is 2.5 hours. So while our session has been going on, the pulsar has covered almost 35% of its orbit. And it has a short 30-second eclipse. The first time I observed with GMRT, I was not sure whether I had this eclipse or not. But lo and behold, I got that. That was also very, very exciting. So I would say these are the three in that order. That is the first pulsar observation with GMRT, followed by the double pulsar discovery and the eclipse discovery, which were the three most exciting observations as far as I am concerned. And if we do detect a gravitational wave next year or the year from that, well, it's not one observation because we have been observing these pulsars for 6 years, but I think that would be the most exciting observations which we have ever done.
So a follow-up on that, you said it's a double pulsar system. Is it also like is it a candidate for gravitational wave detection? Are they like spiraling close to each other?
Yeah, so gravitational wave is already detected from that. Hence that in a double neutron star system, gravitational waves are not directly detected. You don't detect the gravitational wave, but you detect the implication of the gravitational wave. So essentially what the gravitational wave is doing is it is carrying energy, gravitational energy from that system to you. Now the system is losing energy, and that loss of energy is seen as the shrinkage of the orbit. Okay. In the case of pulsar, double pulsar, one can measure this to few tenths of millimeter accuracy, the shrinkage of orbit. Okay, so the precision in double pulsar experiment is unprecedented in astronomy, where usually people talk of factor of 2 precision. In the double pulsar timing, you can measure precisely the position of the pulsar up to a few tenths of millimeter. So the shrinkage of this orbit is predicted by Einstein's general theory of relativity, and the last 16 years of the data, which is there in that paper, has shown that the prediction of Einstein's general theory of relativity are matched exactly by the observations of the shrinkage of this observatory. So obviously, the gravitational waves are being radiated, but this is an indirect detection. In the case of direct detection, you can't directly detect gravitational waves from this because just like double pulsar, there are many other double neutron star systems in the universe. And the gravitational waves from all these double neutron star systems, they superpose on each of other to form what is known as a gravitational wave background. Okay. This is the background which the LIGO observes. So the LIGO observatory, which is a terrestrial detector in Hanford and Livingston in US, and one more detector is coming up in India near Aurangabad soon in another 2-3 years time. So these LIGO observatories, they detect the gravitational waves which are coming from the neutron stars. And but the double pulsar kind of system, they provide a background noise. It's like if you look up in the sky, you see stars, but you also see a faint emission. So for example, if you look towards the Milky Way, you will see a faint distributed diffuse emission and the stars will be seen on top of there. So the gravitational waves which LIGO is detecting is actually coming from black hole mergers. And they are very strong signals, so you can detect them. But they come against a background which is not detectable. And double pulsar system only adds to that background. So you can't detect individual sources there. You can detect a background.
That's really very fascinating. Makes me want to change my field. So again, talking about pulsars, because they have such precise time periods. So these pulses, and we know that they are being used as pulsar clock arrays. Do you have some comments on that? Like their application?
So in pulsars, there are three types of pulsars. One is highly magnetized pulsars known as magnetars, which have periods between 2 seconds to about 12 to 20 seconds, and magnetic fields of 10 to the power 14 Gauss. There are about 30 or so odd sources discovered like that. The bulk of the pulsars have periods of the order of 1 second and 10 to the power 12 Gauss, and that is known as the normal pulsar population. However, out of 2,900, about 400 pulsars have periods of the order of milliseconds and magnetic fields of the order of 10 to the power 9 Gauss. And these are known as millisecond pulsars. So out of all the pulsars, millisecond pulsars, they have proven to be the best possible clocks. And the reason is that since their magnetic field is small, it is very difficult to slow them down. So their rotation can be predicted very well, and their rotation is stable. Essentially, a pulsar slows down because it loses its energy, either as particles or as electromagnetic radiation. Millisecond pulsars are very faint pulsars, and they have smaller magnetic fields, so the particle radiation is also smaller. So they slow down slowly, and their periodicity is very stable. So in 1990s, in fact, millisecond pulsars were being proposed as alternative clocks to atomic clocks, although that no longer stands because the atomic clocks have now become much better. But they are so good clocks. So when you have such fantastic clocks, one of the things which you can do is you can use them to measure small, tiny deviations which can happen because of various other effects. And one such tiny deviation is gravitational waves. Gravitational waves which come from centers of galaxies. So during the formation of the universe, smaller galaxies, they merge together and form larger galaxies and so on. And this is called as hierarchical clustering evolution of galaxies. Now, each of these galaxies harbors a black hole in the center of the galaxy, like our Milky Way has a black hole. And the mass of these black holes is millions or billions of solar masses. Okay, so these are known as supermassive black holes. So when two galaxies with their own black holes, they collide and merge, the black holes become binary. That is, they are captured gravitationally and they go around each other. So these supermassive black hole binaries will produce gravitational waves, which will have very low frequencies. Because a typical orbital period of a supermassive black hole binary like this is of the order of 12 to 14 years. So if you take the inverse of 12 to 14 years, you can find out the frequency. So period is 12 years. You take the inverse of that. The frequency is 10 to the power minus 8 or 10 to the power minus 9, or what we call as nanohertz. Okay. So these supermassive black hole binaries produce nanohertz gravitational waves. And these gravitational waves, when they come near and there are millions of such supermassive black hole binaries in the universe, all their signal again produces a background, like I said, for the neutron stars. This background, unlike the double pulsar kind of background, which is in hertz frequency, this background is in nanohertz. So this nanohertz background gravitational wave, when they come near Earth, they will affect the pulsation frequency of the pulsars by a very tiny amount. And that tiny amount is of the order of tens of nanoseconds or a fraction of a microsecond and so on. So if you have an instrument which can measure these tiny deviations of pulsars which are distributed all across the sky, you can detect the signature of this gravitational wave. So this is an experiment which was proposed by a pulsar astronomer, Don Backer, who incidentally discovered the first millisecond pulsar also in 1990s. And since 2000, these experiments have been operating internationally. There are 4 experiments, one in America called NanoGrav, one in Australia called Parkes Pulsar Timing Array, one in Europe called European Pulsar Timing Array, and the 4th one is in India, which uses GMRT, which is known as Indian Pulsar Timing Array. So these 4 experiments are looking for this tiny fractions of microsecond changes in the pulse frequency to detect the gravitational wave. It's a very hard experiment because, as I said, the period of the gravitational waves is 12 years. So you need 12 years of observation. Okay. And when you do 12 years of observation, you face unexpected problems. Because in our solar system, there is a planet which goes around the sun in 12 years. In fact, there is a planet which goes around the sun in more than 12 years also. So Jupiter and Saturn. Okay. Now, it so happens that we don't know the position of Jupiter and Saturn very well. So Jupiter and Saturn can produce a signal which is very much similar to the signal of gravitational waves. So in the last 4 years, there has been a big discussion with NASA and JPL to try and improve their ephemeris. They didn't have very accurate ephemeris. Okay. So we didn't discover gravitational waves, but we ended up making a much better model of the solar system just because we needed to do that to detect the gravitational wave. Of course, now that has been done. And although the error in the position of the sun So there was a 1 kilometer error in the position of the sun. We have brought it down to something like a few tens or hundreds of meter. Okay, we still need to bring it down to maybe 1 meter or 10 meter, but it is good enough now for us to start looking for gravitational wave, and that is what we have been doing for last 1 year. And lo and behold, last year we did see something which looks like gravitational wave, but we are not very sure whether it is gravitational wave or not. We would probably require a few more years of data to confirm that this signal, which is slowly emerging from the noise, is really the gravitational wave which we are looking for. So here, the pulsars are being used not to study the pulsars or neutron stars themselves, but we are forming giant celestial telescopes made up of these fascinating clocks as a gravitational wave detector out there in the space. Okay. So these clocks are very fascinating, and the general theory of relativity clocks come everywhere. You know, if you try to understand various things, you invoke clocks. So pulsars are the best tools to actually do experiments in gravitational theories.
Wow, I mean, so, I think you saw it on our faces. We were fascinated beyond measure with this whole idea, let alone the amazing way you explained it to us. I would just like to ask you, since you mentioned it also now a few times, about like the Giant Meter Wave Radio Telescope, which is world's largest radio telescope in the specific frequency that it observes, or the specific domain that it aims at. And since you've been also linked with it since so long, would you like to talk about that a bit, and how exactly does it work? Because it's, I mean, to think about a telescope spread across like a radius of 40 kilometers or so, and then still having different telescopes and then combining and still being called a single telescope was extremely foreign an idea, even as college students. So I'm pretty sure that's not something that normally people outside the field would know, interferometry and so on. So would you briefly like to explain that idea and how it's challenging?
Yeah, sure. Actually, I was wondering when you'll come to GMRT, because science is certainly fascinating, but I think GMRT is even more fascinating than science, because first of all, it's a homegrown instrument. Okay, we have built it by our own hands, and I think that is unique, because for Indian science, I think GMRT is a huge leap, and all because of vision of one man who unfortunately is no more with us, Professor Govind Swarup. So no mention of GMRT can be done without mentioning Professor Swarup, who actually built the science of radio astronomy in this country from scratch. Okay, and we talk of make in India today, but Professor Swarup never talked of make in India. He made in India. Right from day one, he made in India. You talked about interferometry. He began his career with interferometry in the Mills Cross in Australia. He was one of the first Indian scientists who used interferometer in Australia, known as Mills Cross, to study the solar phenomenology, the darkening of the limb in sun. And he was one of the students of Bracewell, which those of you who have engineering background will know. Bracewell has done all the Fourier transform theory. So Fourier transform are very important in interferometry. So he was student of Bracewell in Stanford, and the first interferometer, large interferometer which was built, was all built by Bracewell students in a desert in US called Very Large Array, VLA, okay, which is very much like GMRT in that sense. And of course, when Govind came here, he always dreamt of building an interferometer here. He started with a telescope in Ooty, which produced fantastic science and still continues to produce a lot of science. But he always wanted to build an interferometer. So he tried to build one in Ooty and failed on that. Eventually, GMRT came out of that, and that's how GMRT has come about. So very short, brief history of how GMRT has come and the pioneering role of Professor Swarup in building this. What I must emphasize is that all this, whether it is Ooty Radio Telescope or GMRT, is homegrown technology. The structure of Ooty Radio Telescope was done by Tata Consulting Engineers which is an Indian company, and engineers in TCE actually worked from scratch. And in those days when there were no simulation packages, they wrote Fortran codes running into hundreds of lines to do a structural analysis. And it's a very complicated structure, those of you who have seen UT radio telescope. The GMRT dish full simulation and structural analysis was done by Professor Prem Krishna of IIT Roorkee, okay, and his students, one of whom is still a dean in IIT Powai, okay, Professor Ashok Joshi, and so on. So what I want to emphasize is that this is not a design which was imported from US or Europe or somewhere else. It was a design which was built in India. It was built by Indian contractors. The material used was Indian, and it was built in Indian costs. So a telescope like GMRT in US would have cost about 100 times more than what it cost for the taxpayer in the country, 60 crores in 1994. Okay, so typical cost in US would have been something like 600 crores to 1,000 crores at that point of time. So where did that cost saving come from? That came from the ingenuity and innovation of the engineers who worked to produce GMRT and the materials which we used. Okay, and some really path-breaking engineering was done in the design of this particular telescope. So I would say that it's really a feat, and we have operated now this telescope for more than 30 years. It's an international facility which is used by astronomers all across the world and produces scintillating science in various respects. And in the frequency range which you talked about, low frequencies, about 100 megahertz to 1.4 gigahertz, it's the world's largest telescope still. Okay, in future it may not be, because now we have square kilometer array coming, but it is still one of the premier telescopes there. So I think a lot of engineering went into this, and I only talked about the main telescope and the structure, but even the receivers and the digital hardware which was built into the telescope was state of art. Nowadays, embedded control systems are known everywhere, but in 1990, we put microprocessors everywhere inside the telescope control as well as analysis. We did not know that it should be called as embedded control, but I think GMRT is one of the first examples of embedded control all along. Optical fibers were just coming to India in 1990. GMRT was one of the first facility which uses optical fiber over 25 kilometers. So the structural design itself, the smart concept, is a completely novel patented concept in that. So there are a lot of engineering achievement. Science-wise, it's a standard interferometer which Bracewell thought about in 1940s and 50s. And in an interferometer, it's like a Young's double slit experiment. So you resolve by having two slits. So two slits are like your two antennas. The distance between the two slits will give you the separation in fringes. So farther the distance, the smaller is the separation. So you can resolve very small sources out of that. So that's the basic principle of interferometer. But as a single telescope, one way to look at GMRT is that suppose you are sitting on an astronomical source, you are sitting on a star, and you look towards GMRT, which is in a Y configuration spread over 25 square kilometers near Naranggaon. So as you look towards the Earth is rotating, you will see the Y configuration actually rotate. And in 8 hours, cover the aperture, which is of the order of 25 square kilometers. So looking at the star, you are seeing the whole configuration rotate and cover the aperture of 25 square kilometers. Okay. This technique is known as Earth rotation aperture synthesis technique and is used in radio astronomy to have very high resolution observations. The resolution of any instrument, telescope, depends on the wavelength and the diameter or the aperture of the telescope. So it's given by lambda by d. So for an optical instrument, for an optical telescope, even a 3-inch is a very good resolving instrument, because the wavelength is so small that the lambda by d gives you a very high resolution. Radio astronomy, on the other hand, operates at 1 meter wavelength. So to get equivalent resolution, you need kilometers big aperture. And you can't build a single dish of kilometers of aperture. So the interferometry is a cheaper sort of approximation of that kind of an aperture. So both VLA and GMRT are interferometers, and so will be the square kilometer array. In the case of GMRT, our largest baseline is of the order of, as I said, 15 to 20 kilometers. In case of square kilometer array, the largest baseline will be the entire continent of Africa. It will go from southern Africa right up to the northern Africa. So the resolution it will produce will be really fantastic and so on. And its total aperture is 1 square kilometers. GMRT's total aperture is about 30,000 square meter. Okay, so GMRT is 10% of the sort of SK. So it will be much larger telescope there. So as an interferometer, you get high resolution. When you combine the signal from all the dishes together, you get high sensitivity. And that high resolution and high sensitivity is the uniqueness of GMRT, apart from its frequency range, which is 100 to megahertz to about 1.4 gigahertz, and its frequency agility. So you can actually cover seamlessly this whole frequency range. These are the three very, very unique features of GMRT, which still makes it and will continue to make it for few coming years one of the most sensitive telescopes in the world. So I hope I've given you some flavor of that. Of course, this time is too short to explain the things in great detail, but maybe some flavor of the history of GMRT as well as the innovations in GMRT I have been able to sort of convey to you. And again, in the end, I would like to emphasize that the message here is that we can build most cutting edge and the best instruments in the world in the country. It's not that we cannot. Okay. We have the skill set, we have the R&D faculty available in the country. There are premier institutes, including your own institute, IIST, where you have faculty members who have the capability and the skill set to attempt really challenging problems. And one of the things about astronomy is that it presents challenges which you will not find in daily life. So for engineers, astronomy is a really fascinating branch because you can imagine challenges in astronomy which the engineers will have to sort of come up with solutions, which they would normally not bother about, because on the terrestrial domain, you may not be worried about taking up those challenges. But for astronomy, you have to take that. And someday, 10 or 15 or 20 years down the line, the solution which you have found to that challenge in astronomy actually becomes part of the daily life. So it does benefit human beings in the longer run, not instantaneously, but it does benefit human beings in the longer run. More importantly, those of academically minded engineers who love challenges in engineering, I think astronomy is the branch which provides you those challenges.
It has been an explosion of information, sir, and it was so nice to hear you all throughout. As an astronomer and as an engineer, do you have some message for the young audience who are listening to you and looking up to you?
Well, I would say that you should follow the passion which you should follow the thing which you like and which you are very much interested in. You should follow that passion. Many times we do get distracted by financial and other personal matters, which is very natural. I'm not saying that you should not be. You should certainly be distracted by that, but not let that come in the way of your passion. So you may not be able to follow your passion because of some other constraint of yours, but as long as you keep that flame alive inside you, I would, from my experience, I can say that you will eventually end up where you want to end up. Okay. Again, your path may not be a straightforward. Usually life is always a zigzag. Okay. It's not something that I want to become something like this and you become like that. That never happens. So you need to keep your passion alive, your flame alive, and keep working towards it, even if you find there are obstacles in the way. And in fact, I would say the more the challenge is, the better it is, because it makes you a better person. It provides you with a mental attitude and fortitude to overcome challenges. And you can only do unprecedented things or things which no one has done before if you overcome challenges. If you go on a beaten path, obviously things are predictable. Yes, I agree. You are well within your comfortable zone, but you will never be able to do something which is unique. So if you ever want to do something unique, you have to find your own ways of doing that. There is no standard formula, and I would not bore any of you or any of the audience who would listen to this by saying that this is what you should do or that is what you should do. What you should do changes with time. So what was true for my generation will not be true for your generation, may not be true for future generation, because technology has changed, environment has evolved, and so on. So the path which you have to follow would be different. But what remains common is that you should remain true to your passion, even if you are not able to work it in your profession. Okay, so you may be working in something else, but you should keep that profession, that passion alive, and slowly and gradually move towards that. And never think that anything which you have done in life is a waste. Okay, even the greatest of your failure gives you something to learn about. And if you take the lessons from that failure, you would make a success out of something else at the end of the life. So every moment of your life is a teaching experience, and I think you should learn from that. So that's all what I would, this is what I have learned from my own personal experience. And I hope that helps any youngster who would like to sort of follow their heart and their passion to something like that.
Thank you so much for such a refreshing perspective.
And this is undeniably quintessential, sir. The way you've also expressed about the scientific topics as well as the ideas that go around it. Probably, I mean, if there's something else that we missed, you can of course mention it before we wrap. The only question that I would like to ask you again is this thing, because I really remember that there was a really interesting answer that you'd given us. If you allow us, I mean, this is the question that I really wanted to ask, that the importance of bringing and inculcating this multidisciplinary ideas in science, as you mentioned already, like there are different engineering backgrounds which can actually contribute to the whole idea of science a lot more. Do you have a perspective on that, and have you kind of understood this a little more thoroughly, or seen this manifesting a little more thoroughly in the scientific domains today? Because everything is extremely niche right now. If you want to make some big discoveries in something, we have to study at least for 5 years or 10 years or so, it seems. So do you see the scenario of science in India in some sense evolving, or do you have any perspectives or insights on that?
That's a very good and very hard question to answer. So what you have very correctly pointed out is that if you want to do some unique thing, you need to put in a lot of hard work in a particular niche area. So if you just keep flitting from one area to another area, it's like a rolling stone which gathers no moss. So in the end, yes, you will have knowledge about many things, but you would not be able to create some new knowledge. Okay. So the ultimate goal is to be able to be creative and to innovate. For that, you need to stick to a particular area. But it is also true that if you stick to an area for a very long time, then you get saturated in that and new ideas stop coming. So the interdisciplinary nature of the quest is helpful from the fact that sometimes it is good to go away from a field. So I do agree with you that changing every month your interest is not going to help you. You have to stick to something. And when you transit from that something to something else which has started taking your fancy, that transition should be gradual. It should not be a digital transition in the sense that you forget everything about what you did earlier and you start moving to a new domain which you don't know anything about. Okay, so you'll have to start from scratch. So the transition should always be gradual, and it should retain all your prior knowledge and try to apply that prior knowledge to some extent in the new area where you have gone. So if you take that kind of an approach in doing an interdisciplinary sort of exploration, that would be more satisfying and fruitful rather than just changing your area of interest every now and then. Okay. Sometimes this happens by force because in your career, you just finish your PhD and now you're looking for a postdoctoral position somewhere. The area in which you did your PhD, there is no postdoctoral position available. So you have to move. Okay. Same thing may be true in later part of the career. It may be true earlier also that you did your master's and you were interested in cosmology, but now you want to go into biology. Okay. Or you are getting a research position only in biology. So what do you do about it? Okay. So my point is that there is no harm in sort of changing this, but don't do it at the expense of what you have learned. Then you build upon whatever you have learned. And in some sense, knowledge has the same structure, whichever field you apply to it. And as long as you realize that commonness of knowledge and the methodology, I think your switches from one field to another field will also work perfectly fine. As regards interdisciplinary nature of science, I think it's very important that there has to, and it's not just science, by the way. Okay. So to be a good scientist, you should also appreciate other fields. You should appreciate music. You should appreciate arts. Okay. You would be surprised when you can find solutions in areas which don't look at all connected to the scientific field of research which you are doing. Because I think scientific quest is something which is of an open mind. And if you say that this is my specialization, I will not look left, I will not look right, you are actually closing your mind. So that's that kind of closing of mind can actually stop your overall quest for knowledge and so on. So yes, I agree that if you are doing astrophysical research, you cannot necessarily be a good sitar vadak. Okay, you need 8 hours of riyaz for doing to become Pandit Ravi Shankar or something like that. So either you can do riyaz on sitar, or you could go through all the papers in Pulsar astronomy and become an expert on that. You can't do both. Okay, but you can certainly appreciate the thing. You can play sitar a little bit, of course, not at a very high level, but you can still play it. You can use it as a relaxation things, and sometimes that also helps. Certainly, you can appreciate other fields. So interdisciplinarity, I think, is very important to keep your mind open and bring some amount of creativity in your mind, which would not happen if you narrow down your field to a very, very small specific niche area. So you should be interdisciplinary, but not so fast that you don't really actually accumulate any knowledge. So it is a balance. It's a very delicate balance. Why it's all very easy for me to say and very all easy for you to listen. To achieve that balance is not a very easy thing, and you probably require a whole lifetime to achieve that balance. A person who can achieve balance can do wonders.
This was a conversation from the 3rd season of Zeroing In, the science podcast, where we talked about some of the quintessential questions lying in the disciplines of astronomy and astrophysics, discussed more about the open questions, and the truly multidisciplinary approach that it takes to address these ideas. We are very grateful to Professor Joshi for sharing his nourishing insights, excitements of the field, and the love for the subject in a very lucid conversation. On behalf of the Zeroing In team for this episode, which included Rashi Jain, along with the core team of Zeroing In, and I and Naman Jain. Thanks a lot for listening to this episode. We'll be back with a new episode next week with further interesting questions and conversations with eminent Indian scientists from across the world. If you'd like to listen to more such discussions, you can visit us on zeroingin.org or follow us on our Instagram and Facebook handles at Zeroing In Podcast for the latest updates. Until the next time.